Hey everybody, welcome back. This is Chris Neal with another video from Real Science with Chris Neal, where we like to dispel a lot of the bad information that's out there regarding health, fitness, lifestyle, anti-aging, all of that stuff. That's what we do, and that's what we love. I got a message from one of my followers asking me to do a video on Epitalon. So I dug in and dug in and dug in some more, and this is the video I have for you today. So let's just get into it. All right. So what if I told you that your body replaces roughly 330 billion cells every day? And that's not a typo. It's billions with a B. Your blood cells, intestinal lining, skin, and immune cells are constantly being renewed, repaired, and recycled. Meanwhile, other cells, like many neurons and the cells in the lens of your eye, they can stick around for decades or even an entire lifetime. So naturally, people are interested in anti-aging, or they start asking a big question. Can we support cellular renewal without accidentally increasing the risk of cancer? So that's really the question that brings us to telomeres, telomerase, and a peptide that often shows up in longevity conversations, Epitalon, also called epithalin, depending on what you're reading. Today, we're going to break down what the science suggests, what it absolutely does not prove yet, and why longer telomeres is not as simple as it sounds. Um, let's start with the sheer scale of what your body is doing right now. I always like to take a 30,000-foot view. A recent estimate puts the human body at roughly 30 trillion cells. Although that number differs, obviously by body size and by sex. A representative adult male may have closer to 36 trillion, while a representative adult female can have around 28 trillion. And every day, around 330 billion cells die and are replaced. But here's an important correction to a popular internet talking point. This does not mean that your entire body gets completely replaced every 90 days. That's not how biology works. It's more like a city that's under nonstop construction. Some buildings get renovated every week. Some roads are resurfaced every few years. And some historical landmarks remain standing for generations, okay? So for example, red blood cells, they circulate for about 120 days before being replaced. Your intestinal lining turns over extremely fast, often within days. Skin cells are continually shed and renewed over weeks. Many liver cells can regenerate over months. Skeletal muscle fibers can persist for sometimes years. And many cells in your brain and your eyes may last for life. So your body's not hitting a giant biological reset button every 3 months. Instead, it's managing billions of cell-specific maintenance schedules all at the same time. And that cellular maintenance program is where telomeres come in. So think of your chromosomes kind of like shoelaces. At the ends of the shoelaces, you have those little plastic caps that stop them from getting frayed, right? Telomeres often describe themselves, or they're often described as the biological equivalent of those little caps on the shoestrings. They are repetitive DNA sequences at the end of the chromosomes that help protect genetic material during cellular division. Every time many cells divide, telomeres tend to get a little shorter. They get kind of snipped. Eventually, if telomeres become critically short, the cell may stop dividing. So in a way, it's kind of like an alarm clock. They enter a state called senescence, or they just die. That sounds bad at first, but it actually is part of a protective system. Cellular senescence can be a biological do not proceed sign, a way to stop damaged or unstable cells or old cells that are too old from endlessly replicating. Now, there's an enzyme that's called telomerase that can help rebuild and the activation of telomerase rebuilds telomeres. And this is where the longevity world gets very, very interested. If shorter telomeres are associated with cellular aging, then wouldn't activating telomerase be a way to fight aging? Eh. Biology loves a plot twist. So this is where the detail comes in. So this is this whole discussion, this whole video is a perfect video because I believe that things are not always as simple as they seem. And if things do come off really simple and really straightforward, then you're probably missing something. And this is the perfect way to describe that. So telomerase may be helpful in certain contexts, but it's also active in the vast majority of human cancers. That doesn't mean telomerase automatically causes cancer, and that distinction matters. Telomerase is generally considered necessary, but not sufficient for many cancer cells to begin dividing indefinitely. Cancer usually requires additional genetic and cellular changes, things like disrupted tumor suppressor pathways, abnormal growth signals, DNA damage, and immune evasion. Still, telomerase can give cancer cells a major advantage. It helps them overcome the normal limit on cell division. In most adult somatic cells, the body keeps telomerase activity relatively low. Now, that may come with a trade-off, gradual telomere shortening over time, but it also acts as a barrier against unlimited cell replication. So telomerase sits right in the middle of a major biological tension. Too little telomere maintenance may contribute to degenerative problems. Okay? Too much sustained telomere maintenance may help the wrong cells survive. And that is the telomere paradox. But before we go further into the telomere paradox, there's one important concept we need to add in, and that is, I told you this was going to get complicated, that is the Hayflick limit. So going back to the early 1960s, scientist Leonard Hayflick discovered that many normal human cells grown in a lab do not divide forever. And instead, they can divide only a limited number of times before they permanently stop dividing. For certain human cell types, especially the fibroblast cells that Hayflick studied, that limit is often described as roughly 40 to 60 divisions. But that number is not a universal number for every single cell in your body. Different cell types, like we talked about, have different lifespans, division patterns, and regenerative capacity. So think of the Hayflick limit less as one hard number and more as a biological principle. Most ordinary body cells are not designed to replicate indefinitely. So why does this limit even exist? Well, every time a cell divides, it has to copy its DNA. But the very ends of the chromosomes, the telomeres, like we talked about, are difficult to copy perfectly. So with repeated cell division, telomeres tend to become progressively shorter and shorter and shorter. Eventually, they can reach a critically short length, and at that point, the cell essentially receives a message that says, stop, it's no longer safe to keep dividing. The cell may enter a non-dividing state called cellular senescence, or it may undergo programmed cell death, also known as apoptosis. Now, that may sound like bad news, but it's also an essential safety feature. It helps prevent cells with accumulated damage from endlessly copying themselves and potentially becoming dangerous, like cancer. Now, there are some important exceptions here. Some cell populations need to renew themselves throughout life. Stem cells in tissues like bone marrow, skin, and your gut can maintain regenerative capacity far beyond what we see in typical somatic cells. One reason is that they can activate or deactivate their telomerase to help manage their telomeres. Germline cells, the cells involved in producing sperm or eggs, they also use telomerase activity to help preserve their genetic material and continuity across generations. And then there are cancer cells. Many cancers activate telomerase, allowing cells to bypass the normal division limit. So that does not create cancer by itself. But once a cell has accumulated, other cancer-promoting changes escaping the Hayflick limit can allow that cell to keep dividing far beyond its normal lifespan. So the Hayflick limit is not just a limitation of aging. It's also one of the body's built-in anti-cancer brakes. And that brings us back to the central question. If we try to influence telomerase and telomeres for longevity, how do we support healthy tissue renewal without releasing the brakes on damaged cells? So that's the paradox. Where does Epitalon come into all of this? So Epitalon is a synthetic peptide that has been discussed for anti-aging research for its potential effects on cellular aging, circadian biology, immune function, and possibly telomerase-related pathways. It's touted to activate telomerase that lengthens your telomeres. But here is the responsible, non-hype answer. The evidence base is still limited, especially when it comes to long-term human outcomes. There is scientific interest in whether compounds that influence telomerase might support healthier aging, sure. Some pharmacologic telomerase activators have shown modest and temporary increases in telomerase activity in certain studies. Okay, so that's good. And short-term studies of some telomerase targeting compounds have not shown an obvious increase in cancer incidence over limited follow-up periods. So that's good. Okay. But no clear signal in short-term data is not the same thing as proven safe for years of use. That's a massive difference. The central unanswered question is whether a modest temporary increase in telomerase activity in normal cells behaves differently from the persistent high-level telomerase activation seen in cancer cells or inherited long telomerase syndromes. It probably just does behave differently, but probably is not the same as, well, we know, right? So here's a useful way to think about it. In cancer, telomerase activation can be high, persistent, and paired with multiple other mutations that push a cell toward uncontrolled growth. A pharmacologic compound, on the other hand, may produce a lower level or temporary signal in otherwise normal cells. Those are not necessarily the same biological situation, right? Plus, telomerase may do more than simply just lengthen telomeres. Researchers are investigating potential non-telomere roles involving mitochondrial function, cellular stress responses, inflammation-related signaling, and gene regulation. That means the story is bigger than simply telomerase on equals youth. But it also means the biology is more complicated than any one supplement, any one peptide, or any one podcast clip that can capture. If you're interested in health optimization, peptides, and longevity, the big lesson here is not telomerase or telomeres are bad. And it's definitely not telomerase is the fountain of youth either. The real lesson is this: aging is not caused by one switch. It's an interconnected system involving cellular turnover, mitochondrial function, inflammation, immune surveillance, DNA damage, sleep, metabolic health, muscle mass, cardiovascular fitness, and much, much more. Never ends. And honestly, the least glamorous interventions are still some of the most powerful. Resistance training to preserve muscle and metabolic health, cardiorespiratory fitness, adequate protein and nutrient-dense food, sleep and circadian consistency, hormonal balance, avoiding smoking, managing body composition and insulin resistance, staying up to date on preventative medical care. These strategies may not sound as futuristic as a peptide with a cool name, but they have something extremely valuable behind them. a much stronger track record of benefit and safety. Epitalon and telomerase biology are fascinating areas of research. There may be real therapeutic potential in understanding how to preserve tissue function and cellular resilience as we age. But when the conversation turns to long-term telomerase activation, we need intellectual honesty. The short-term evidence is not the same as long-term proof. The absence of an observed cancer signal is not the same as zero risk. And longer telomeres, longer telomeres are not automatically better. It's to understand the trade-offs, respect uncertainty, use evidence and scientific understanding as your compass, and build a lifestyle that gives your cells the best possible environment to do what they already do remarkably well, which is to keep you alive. So, like all of the videos and all of the things that I discuss, I implore all of you to go seek out a medical professional that understands the nuances and complexities of these, because if I tell you, if you don't do this for a living, it's a lot. It's a lot. So please find someone that you trust, find someone that you can work with that understands these things to this kind of level, and have at it. Fight the good fight and anti-age. It is worth it. I'm telling you. If you enjoyed this kind of breakdown, hit like, hit subscribe, let me know in the comments, share this with someone that you've been talking about peptides and health and fitness with. Also, if there are other topics that you'd like for me to discuss similar to this one, please let me know. Share in the comments. Thanks for watching, and I will see you on the next one. Stay healthy.